Good morning to lecturers and fellow friends. Welcome to my presentation. And my project is about the expert system for diagnosis heart disease. My name is Ang Zhen Long, and I'm presenting this project on behalf of our team Li Pei Lo, JINSEN, Aaron, Josh, and this our TES expert system course project. Our system employ the knowledge approach for diagnosis disease, placing the special emphasis on medical transparency and clinical interpretability. So for the introduction and proper statement, for nowadays, the heart disease is truly global health crisis. According to the World Health Organization, it caused 17.9 million deaths annually, making the leading of mortality worldwide. Such a high-scale accuracy diagnosis is absolutely critical. However, current medical expert system facing significant limitations because many model systems using black box machine learning models, while they might achieve high accuracy, but the doctors can't understand why particular diagnosis was made. There's no transparency. Second, there's poor documentation of knowledge resource. May system not clearly show whether their diagnosis rules come from. But the third is the lack of transparency creates a trust issue. Healthcare provides the natural hesitant to adopt system they can't understand or validate. The fourth one is without the clear documentation, is difficult to validate those systems against the established medical literature and clinical guidance. Those limitations motivate us to develop a different kind of system that prioritize the transparency and explainability of the ground up. So for the objective, we established 4 clear research objectives for this project. For the objective one is develop a transparency spongy expert system which is standardized, a decision fully explainable at each step, no black box involved. For objective 2 is construct an evidence-based knowledge base using the rules driven from peer-reviewed medical literature with each rule clearly traceable its original resource. For the third objective, validate the proposal using the dataset and demonstrate the quantitative accuracy against those state-of-art methods. For the fourth objectives is design and implement a professional user-friendly web interface suitable for real-world clinical decision support. For the system architecture, we are using the classic multi-fuzzy interference system with 4 stages. So stage 1 for verifications. We collect about 13 clinical input parameters. This include the patient demographic, like age and 6 symptoms such as chest pain, type of exercise including angina, vital sign including the blood pressure and heart rate, label like cholesterol and fasting blood sugar, and diagnosis test result from ECG and exercise stress test. Each of those scripts numerical values is converted into the Fuzzy members degrees. For example, cholesterol level of 230 isn't that high or normal, but we have 70% membership in the borderline categories, 30% membership in high. These capture the greatest natural medical risk. So for the stage 2, this part of our system, we evaluate 50 Madani Fuzzy rules in the parallel. Each rules check the condition against the Fuzzy inputs. Those rules come for the peer review literatures. For the stage 3 aggregation, all the activist rules are combined using the Fuzzy unit operation to create a complete output. For the stage 4 diffusifications, finally we convert this Fuzzy output into the CRIPS risk score from 0 to 100, which categorized as low, medium, high risk for the easy clinical interpretations. Those key advantages here, every stage transparency, and the doctor can trace actually how the system arrived these conclusions. For the knowledge representation for the age, we define the 3 percent based on the WHO 2020 guidance, young, middle, and old. For the young is about the 20 to 45, the middle is 35 to 65, and the old is spent to 55 to 80. You can see there's a overlap. For example, 60 years old patient doesn't belong to secretary. Maybe the particular membership in both middle and old. For the cholesterol, we apply the same principle cholesterol following the Mayo clinical guidance. The normal is 100 to 240 mg and borderline 200 to 260 mg, and the high is 240 and above. So we also have the overlapping. So we can see the rules at here. So why does it make it the medical sense? So justification will establish the a leader patient with cholesterol level higher than the 240 milligrams per deciliter have threefold increase of the coronary artery disease according to the American Heart Associate guidance. These rules just make up the back end indicate the research doctor can actually see the paper rule come on verifications is medical justification, and this how we means the transparency. For the validation result, we evaluate our system on the UCI prevalent heart disease dataset, which include the dataset from 303 patients, is widely used for benchmark in heart disease research. Our model achieved about 93.4% correctly the classification 283 patients, and the sensitive received about the 94.1%, indicating the strong ability detecting true heart disease cases, while sensitivity was 92.6% efficiency identifying the help patient, reducing the unnecessary clinical interventions, although our accuracy is slightly lower than the best reports system. The key advantages of our approach lies on the full transparency. Every diagnosis decision is driven by explicitly defined for the rules, each traceable peer-reviewed medical literature in clinical practical. This level of explicitity is often greater than the marginally against accuracy, making our system more suitable for each real-world medical decision support. So about our system implementation, our technology stack is built on the Python, and we use Git per G as our Madani inference engine. This well-tested library widely used for the system research. So we're using the Flask as our web framework. So the web interface includes the several important features, and we can input from with the real-time validation. The system won't be that doctor invalid values. So their visual risk display the color code result and a program bar for easily interpretations. Most importantly, the system provides the detailed explanation showing actually which rule fired and why along the medical papers are support those rules. And we have prepared a separate demo video for showing the system in action with the high-risk patient case. Okay, to start our program, we need to type this command, and will provide us a link. So after clicking the link, it will jump to this page. So as we can see, I already input the data for the high-risk patients. So let's see how it goes. So you can see that the result have come out. So you can see the key risk factor is right here. It is called top contribution rules and the recommendation right here. So we can see the fired rules right here. So this is a total the summary of our demo lah. So for the conclusion, in summary, we have delivered a transparent for this expert system with fitting evidence-based rules derived from the peer review literature. The system achieved about 93.4 accuracy on the UCI equivalent dataset while maintaining the full accessibility and traceability for every diagnosis decision. We also implement the professional web interface suitable for clinical decision support. For future work, we are planning to expand the rule-based, conduct clinical validation, and integrate the system with electronic health records. Overall, this work shows for this expert system remain the high relevant in medical diagnosis, offering a level of transparency and clinical trust that a black box mode cannot provide.